Okay, so basically today we will continue with chapter 5, part 3. Yeah? So this is the second last part for chapter 5. Okay, so we will have another class session lecture for chapter 5 next week. Okay, so for chapter 5, part 1 and part 2, we have covered this last week. And basically for part 1 and part 2, it is fully theory. Okay. So for part 3, today we will cover for part 3. So part 3 will is consists of the transmission and data communication and also multiplexing. So we will cover two things in part 3, which is the transmission and data communication and also on the multiplexing. Okay, before that, for this part 3, for those who already downloaded the lecture notes, this one, before yesterday. Okay, so you need to download it again because yesterday I've uploaded the latest one, the latest slide for chapter 5 part 3. Okay, so sesiapa yang dah download sebelum ni minta untuk download semula. Okay, so this is a new slide. Okay, so okay, for transmission and data communication, okay, it can be accomplished in two modes. So the first one is in parallel, the second one is in serial. So before that, okay. Okay, so parallel and also serial. So in parallel mode, okay, in parallel mode, multiple bits can be sent with each clock tick. Okay, so for parallel, you will have sender over here, and then you will have a recipient here. Okay, and the data can be sent multiple, okay, multiple bits at a time. Okay, compared to the serial mode, for the serial mode, you have the sender and you have the recipient. Okay, for serial mode, okay, you only can send one bit at a time. Okay, so this is the difference between the parallel mode and also the serial mode. So this is the parallel, this is the serial mode. Okay, so for the serial mode, we can further divide into three. So we have a synchronous, and also the isochronous. Okay. So let's look at the first one, which is the parallel transmission. So parallel transmission, just now I already told you that you can send more than one bits at a time. Okay, so since you can send more than one bits at a time, over here we can send up to 8 bits altogether. 1, 2, 3, 4, 5, 6, 7, 8. So 8 bits, we can send 8 bits at a time. Okay, so since we can send 8 bits at a time, so the advantage of the parallel transmission is of course in terms of the speed. Okay, because you can send more bits at a time. But the thing is, because since you can send the bits, multiple bits at a time, so you will need more lines. Okay, so over here, actually the number of wires, this is the lines or the wires. The number of wires depending on the number of bits. Okay, so if you want to send this n, so if you want to send 8 bits, then you need to have 8 wires lah. Okay, so since if you want to send more bits, then you need more number of wires, and because of that, this parallel transmission has a disadvantage in terms of the cost, because you need to use a lot of wires. Okay, and that's why this parallel transmission is only limited to short distances. We usually don't use parallel transmission for long distances because we want to reduce the cost. Okay. So the next one is the serial transmission. Okay, so serial transmission, you can only send one bit at each clock. Okay, so you only need one wires. Okay, so the advantage is that the cost is lower compared to the parallel transmission. Okay, because you only need one line or one wires. Okay, but the thing is the disadvantage is in terms of speed lah, of course. And another one for the serial transmission, the input is usually in the form of parallel, like 0, 1, 1, 0, 0, 0, 1, 0, like this. So you need to have a parallel to serial converter in order to convert it to series. Okay, so this data over here, you need to have a parallel to serial converter in order to convert it to 0, 1, 1, 0, 0, 0, 1, 0. Okay, then only you can send this data through a single line. And then you need to have a serial parallel converter at the receiver in order to convert this data back to parallel, like this 0, 1, 1, 0, 0, 0, 1, and 0. Okay, so this is the difference between parallel transmission and also serial transmission. And for the serial transmission, we have a synchronous, and also isochronous. Okay, so we will look into this one by one. Okay, so for the first one, the asynchronous transmission. Okay, so you can see that for asynchronous, okay, based on the name itself, you should know that the timing of the signal is unimportant. Okay, so why we said that the timing of the signal is unimportant, because in order to determine which one is the data, we have the start bit and we also have the stop bit. Okay, start bit is that you need to have a one more bit at the front, which is the bit 0. Okay, and then we need to have another one bit, which is the bit 1 at the end of each part. So this is how the receiver actually determine the data. Okay, so for example, for this one, we have 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. So you want to send 8 bits. Okay, so you should know, remember this 8 bits is equals to 1 byte. 8 bits equals to 1 byte. So when I said 1 byte, you should know that 1 byte is 8 bits. Okay, so for this example, the sender want to send one frame. This one we call as a frame. Okay, so one frame consists of 8 bits, and you need to have another 2 additional bits, which we call as the start bit, bit 0 at the front, and also the stop bit, bit 1 at the end. Okay, and for a synchronous transmission, you could have a gaps here. Okay. Okay, there may be a gap. Okay, so it depends. Sometimes you don't have the gap. Okay, so how this again, I repeat, how this receiver actually determine which one is the data is based on the start bit and the stop bit. Okay, so this is for a synchronous transmission. Different to the synchronous transmission, this is synchro. Okay, synchronous transmission. If you look at here, the figure here, the stream of bits here is combined into frames. This is what we call as frames lah. One frame, second frame, third frame, fourth frame, fifth frame. Okay. So for synchronous, the difference is the bits here are sent after another without the stop bit or the start bit or even a gap. Okay, there is no start bit, there is no stop bit, or you don't also have, there is no gaps. Okay, so how does receiver determine the data is by calculating it one by one. Okay, so it is the responsibility of the receiver to group the bits. Okay, to group the bits by frame. Okay, so the receiver actually needs to calculate bit 1, 2, 3, 4, 5, 6, 7, and 8. Then the receiver can actually determine that this is one frame. Okay, so the advantage of the synchronous transmission is actually in terms of speed lah. It's a high speed transmission because you don't have the additional bits and also you don't have the gap here. Okay, so the asynchronous, you have the start bit, stop bit, and also the gap. For this one, the stream of bits is simultaneously. Okay, so the accuracy of the received information, it depends on the ability of the receiver to keep an accurate count of the bits. So this is what I said just now. The accuracy of the information depends on the ability of the receiver to count the bits. Okay, count it one by one. Okay, 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so this is the difference between a synchronous transmission and also the synchronous transmission. And the last one, we have the isochronous transmission. Okay, isochronous transmission, it is actually similar to synchronous, but for synchronous transmission, you cannot use it if the application is in real time. Okay, where you have uneven delays between frames. Okay, so the frame, this is the frame, this is the frame, one frame, second frame. So in between there will be a delay. Okay, so this delay, the delay is fixed, meaning the delay is the same between each frame. But if you have the delay between each frames are not uneven, meaning different delay, okay, so you cannot use synchronous transmission. So you need to use the isochronous transmission. Okay, so this isochronous transmission will guarantee that the data arrive at the fixed rate. Okay, and it will make sure that it is occurring at the same time. Okay, so this is basically for the transmission in data. So what you need to know is that we have parallel, we have serial mode. For serial mode, we have three, asynchronous, synchronous, and the last one is isochronous. So you should be able to differentiate all of these, okay, and explain. Okay, so the second section in part 3 is on the bandwidth utilization or multiplexing. Okay, so when we talk about bandwidth utilization, it actually means that the wise use of the bandwidth. Okay, so this is the bandwidth. Okay, this is the link or this is the channel. Okay, you have the input, output, and in between here is the channel. Okay, so this is what we call the bandwidth. Okay, the bandwidth of the channel. So bandwidth utilization is how can we actually achieve maximum efficiency, okay, for the channel, meaning the wise use of the available bandwidth here. Okay, so in order to make sure that we have the maximum utilization of the bandwidth, we can use multiplexing and also spreading. So multiplexing is the process to achieve efficiency. Okay, And spreading is to achieve privacy and anti-jamming. What is anti-jamming? Is actually to protect from interference. Okay, so we will focus on the multiplexing. Okay, so what I'm sure that all of you already heard about multiplexing before this. Okay, so basically, what this multiplexing does for multiplexer, so you have multiple inputs and you want to make it the output is only one line. Okay, so this is the process of multiplex. Okay, multiplexing. So whenever the bandwidth of a medium linking two devices is greater than the bandwidth of the device, the link can actually be shared. Okay, meaning this link, even though you only have one link, but the thing is, if the bandwidth is bigger than the actual, then you can actually share this link. Okay, so that's why even though you have multiple inputs, more than one input, but you can actually share using one link. Okay, so multiplexing is a set of techniques that allows the simultaneous transmission of multiple signals across a single data link. Okay, multiple signals, but you want to share it to be sent in a single data. So the demultiplexer, this is the demultiplexer. So it is the opposite of the multiplexer lah. So it will convert from a single data link to a multiple output. Okay, so the multiplexer actually combines n lines and number of lines of streams into a single stream. Okay, so it is actually many to one. And the demultiplexer, the demux here is the opposite of the multiplexer lah. So it separates back the stream into its component transmissions. Okay, so for multiplexing, we have several types. So the first one is the frequency division multiplexing. The second one, we have the wavelength division multiplexing. The third one is time division multiplexing. So this, the short form is FDM. This is WDM. And this is the TDM. Okay, so please take note that for the FDM and WDM, these two are analog multiplexing. The third one, time division multiplexing, is the digital part. Okay, so now let's look at one by one. What is FDM, WDM, and also the TDM? Okay, so for frequency division multiplexing, okay, directly go here. So for frequency division multiplexing, so you have over here this figure. So you have three signals. You want to send three signals. Okay, and you want to multiplex these three signals. So what happens is that this is the multiplexer, the gray one, the gray part here in this kind of like a box here. This is the multiplexer. Okay, so this is the process that happens in the multiplexer. So what happens is that this the first signal will go to the first modulator. Okay, basically inside the multiplexer you have the modulator. Okay, I hope you still remember your modulator. Okay, modulator, you will have two inputs, FM and also FC. This is your FM because this is your information, the original information. This is FM, and then you have the FC. Okay, so for over here, we have three modulators. So we have FC1, FC2, and FC3. Okay, FC1 is F1 lah. Okay, it's just that over here is the carrier F1. So I just write FC1, FC2, and FC3. Just so that you're aware that this is actually the carrier frequency. Same as what you have learned in chapter 2 and 3. Yeah, so For frequency division multiplexing, the carrier frequency, okay, the carrier frequency here is different. So if you look at the first, for the first signal, the carrier frequency, we use a lower frequency. Okay, for modulator 2, you can see that the FC2, the frequency is higher compared to F1, FC1. And for FC3, we set the carrier frequency to be higher compared to FC2 and FC1. Okay, so this is the output of the modulator. Okay, so you will have something like this. Okay, this is the envelope, the output of the modulator. Okay, so you can see the difference. Okay, so in terms of frequency, because the FC, the carrier frequency is different. Okay, so for frequency division multiplexing, the parameter that is affected is the frequency. So go through the summation here. So the output of the multiplexer, you will have this kind of signal. Okay, so this is the process of frequency division multiplexing. Okay, so this one, just now this is the multiplexer at the input. This is the demultiplexer. Okay, so at the demultiplexer part, this is the signal that you have multiplexed before. And this gray box here is the demultiplexer. Okay, so inside the demultiplexer, you have a filter. Okay, and you have a demodulator. Okay, so remember your demodulator. Okay, so it is the opposite. The function is the opposite of the modulator. Okay, so this demodulator will demodulate this signal to get back the original signal. Okay, so you have three signals. Okay, so this is the process of the frequency division multiplexing of the FDM. Okay, so now let's look at this example. Okay, so this is a new slide. For those who already downloaded the previous slide, the old slide. So in the old slide, you don't have this text. You only have the answer here. Okay, so this one I just add. Okay, so please download the new slide. So for example one, assume that a voice channel occupies a bandwidth of 4 kilohertz. So you have you have voice channels with a bandwidth of 4 kilohertz. So this is the bandwidth of the voice channel. Okay, 4 kilohertz. So you need to combine 3 voice channels. So you have 3 voice channels and you want to combine it into a link. So the link, this is the link. This is the link. Okay, or the channel. So it stated that the link has the bandwidth of 12 kilohertz. So the bandwidth of the link is 12 kilohertz. And it varies from 20 to 32 kilohertz. So the question asks you to show the configuration using the frequency domain. Assume there are no cut bands. So this is the answer basically. So you have 3 voice channels, all with the bandwidth is 4 kilohertz each. So you want to multiplex these 3 signals, okay, so that it can be sent into a single link. Okay, so the first thing that you need to do, you need to modulate the signal. So at the output of the modulator, you will have the frequency of the signal will be changed because previously, remember, you have different carrier frequency. So that's why we set different carrier frequency here. So this is lower frequency, medium frequency, and high frequency in order to set the frequency at the output. So that's why over here, for the first signal, now the output, the frequency actually varies from 20 to 24 because the FC1 is lower. Okay, so for signal 2 over here, okay, so we use a higher FC1 compared to higher FC2 compared to the FC1. So that's why at the output, the frequency is 24 to 28. Okay, and the third one, the frequency is 28 and 32. Then you combine this, okay, then only you will get these signals. Okay, so this signal actually varies from 20 to 32. Okay, varies from 20 to 32. Okay, so then only you can send the signal through the link that you already have. Okay, so this is at the multiplexer part lah. Okay, so the multiplexer, you have the bandpass filter and it will demodulate the signal again to get the 3 signals separately. Okay. The second example, this one. Okay, so this is also a new slide. Previously, you don't have this. You only have this answer over here. Okay, so example 2 stated that you have 5 channels. Okay, 5 channels, each with 100 kilohertz bandwidth, are to be multiplexed together. Meaning that over here you have the multiplexer and you have 5 channels. Okay, so this is what it means by 5 channels. Okay, and each channel has a bandwidth of 100 kilohertz. Okay, and the question asks you to draw the output of the multiplexer. Okay, so what is the minimum bandwidth of the link, or if there is the need for a guide band of 10 kilohertz between the channels to prevent interference? Okay, so by right, you should draw the signal first, and then you can calculate the bandwidth. Okay, so over here you have 5 channels with 100 kilohertz each, meaning the first channel has 100 kilohertz, second 100 kilohertz, third 100 kilohertz, fourth 100K, and the fifth one 100 kilohertz, the bandwidth. So at the output of the multiplexer, what you should have is that you should have this all 5 signals. Okay, channel 1, channel 2, channel 3, channel 4, and channel 5. Okay, so the bandwidth of this channel is 100 kilohertz. Okay, like this. And it already stated that you should have a guide band of 10 kilohertz. So by right, in between each frames here, you should have a guide band of 10 kilohertz. Okay, so in order to determine the minimum bandwidth, then you just calculate 100 kilohertz plus 10 plus 100 plus 10 plus 100 plus 10 plus 100 plus 10 and plus 100. Okay, so basically it is 5. So you have 5 signal, 5 multiplied with the bandwidth 100 kilohertz plus the guide band. So the guide band, you have 4 guide band, 1, 2, 3, and 4. Okay, so plus the guide band. So one guide band is 10 kilohertz. Okay, so basically the overall bandwidth that you should have is 540 kilohertz. Okay, so the next slide. This is the just the application of the frequency division multiplexing. Okay, so the FDM, you should know that one of the application is that it is used in analog carrier system in order to maximize the efficiency of the infrastructure. Okay, so this is just an example. So over here you have the 12 voice channels. Okay, you want to send 12 voice channels with a bandwidth of 4 kilohertz each. Okay, so these channels is multiplexed using FDM, frequency division multiplexing. So by right, you will have the output in a single link. Okay, so this the link here, the bandwidth is 48 kilohertz. Okay, because it's actually 12 multiplied with 4. So you should get 48 kilohertz. Okay, and then you have multiple multiplexer over here. Okay, so this is just to show you the application for the analog carrier system. Okay, so you multiplex once, then you have a group here, and then you have another 5 groups, and then you multiplex again. So this will become the super group, and then the super group add with another 10 super group, then you become a master group. Multiplex with another 6 master group, you will get the jumbo group. Okay, so this is the example of the process of frequency division multiplexing in analog carrier system. Okay, so the next type of multiplexing is the wavelength division multiplexing. Okay, so the wavelength division multiplexing, it is used in fiber optic cable. The difference is WDM is used in fiber optic cable. Okay, so everyone knows what is fiber optic cable. So fiber optic cable, the data rate is higher compared to the conventional cable. Okay, so when you deal with fiber optic cables, the source signal will be light signals. Fiber optics, the signals is light signals. So the light signals will be transmitted through fiber optic channels. Okay, for this kind of application, you need to use the wavelength division multiplexing or WDM. Okay, so compared to FDM, now the parameter that we look into is the wavelength. So lambda 1, lambda 2, and lambda 3, this is the symbol for wavelength. Okay, so you have three, for example, you have three signal, you want to multiplex it together. So we look into the wavelength. So the output of the multiplexer, okay, so it will become lambda 1 plus lambda 2 plus lambda 3. Okay, so the process of the wavelength division multiplexing actually follows the concept of prism. Prism, I hope that everyone knows what is prism. You have seen this before at school. Okay, the yang tiga segi tu. Okay, so it is a prism. Okay, so just now I already told you that wavelength division multiplexing is used in fiber optics. With fiber optics, the signal is light signal. Okay, so you know that the light beam can be bent using a prism. Okay, so that's what is stated here. Combining and splitting of the light sources are easily handled by a prism. Okay, so this prism can actually bend the light beam. Okay, so this is the first light beam, second light, third light beam. Okay, so this prism can actually bend this signal in order to become a single signal like this. Okay, so WDM actually follows the concept of a prism. Okay, so this third multiplexing is the time division multiplexing. So TDM is a digital multiplexer. Okay, for the previous multiplexer, the signal are in analog. Okay, but for this one, the signal are in digital. So when we talk about digital, then the signal is in binary lah, 0, 1. Okay, so the TDM can be divided into two. The first one is synchronous TDM. The third one and the second one is statistical TDM. Okay, so I will explain further about this in the last slide. Okay, before that, I want to explain on the concept of TDM. Okay, for TDM, over here, look at this figure. So you have 4 channels. This we call as channels. Okay, so we have 4 channels, channel 1, 2, 3, and 4. So this channel 1, for example, from PC1, you want to send a stream of bits, a stream of data. So you have, for example, you have 0, 1, 0, 1. Same as this one, you have 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1. Okay, so you want to send this data in a single link. Okay, one link. So you need to have a multiplexer. So what happens in time division multiplexing is that how it multiplexes this data is actually this is a link. This we call as the frame. Frame. This is frame 1, frame 2, and frame 3. So if you look at here, for frame 1, it will take 1 bit from channel 1, 1 bit from channel 2, 1 bit from channel 3, and 1 bit from channel 4. Okay, so what happens is that 1 bit from channel 1 is 0, 1 bit from channel 2, 1, 1 bit from channel 3, 1 bit from channel 4. And then the second frame, it will take the second bit from each channel. So 1 bit from channel 1 is 1. 1 bit from the channel 2 is 1. 1 bit from the channel 3 is 0. 1 bit from the channel 4 is 0. And the third frame, it takes the third bit. So this is 0, 0, 1, 0. Okay. So this is how the data is sent through the link. Okay. So from parallel data like this, you have a series data. And then you have the demultiplexer to get this data back. Okay, so you have 101, 1011, 1100, and 100. Okay, so this is the process of time division multiplexing. Okay, so this is what I explained just now. Okay, so you have 3 channels. This one you have 3 channels. 3 channels. Okay, channel A, channel B, and channel C. The output of the multiplexer, before that, the data from each line. Okay, this is P. So the output of the multiplexer, for the frame 1, you will have 1 bit from A1, channel 1, 1 bit from channel 2, 1 bit from channel C. For frame 2, 1 bit from channel 2, 1 bit from channel 1, 1 bit from channel 2, 1 bit from channel 3 or channel C. Okay, so you will have something like this. Okay, and this we call as frame 1, frame 2, and frame 3. Okay, so the duration of the frame is equals to T. Okay, so basically one frame we have 3 slots, depending on the number of channels. This is what we call as slots. Slots. Okay, so this time slot duration is actually T over 3 lah, because you have three slots. But if you have 4 channels, here, then your one frame you will have 4 slots. Okay, then your time for one slot is T over 4. Okay, so that's why to calculate the output time slot, we use this formula T over N. T over N. N is the number of channel or the number of slot. Okay. So now let's look at this example. Okay, so in the previous, in the old slide, you don't have the solution here. Okay, so I already give you the solution, but so you need to, even though you already have the solution, but it depends on you lah, whether you understand it or not. Okay, so let's try this one first. For given here, for 1 kilobits per second connection. Okay, meaning that you have 4 channel. Okay, each channel, you have 1 kilobits per second. Okay, so a unit is 1 bit. The first question, find the duration of 1 bit before multiplexing. How can we answer this? The answer here is already given here. The answer is actually 0.001 second. But what does the question actually means? Okay, so for this one, actually, okay, it already stated that you have 1 kilobits per second, meaning that you can send 1 kilobit in 1 second. Okay, 1 kilobits you can send in 1 second. Okay, so the question is the duration of 1 bit before multiplexing. So the question actually asks you the duration for 1 bit. Okay, so 1 kilobit is 1 second. So 1 bit is 1 divided with 1K. So you should get 0.001 second. So this is the answer for A, this one. Okay, so the question actually asks you the duration for 1 bit. Okay, faham eh? Okay, so I assume that you understand. So the second one, the transmission rate of the link. Okay, so this is you have 4 channels. Okay, and the output of the multiplexer, you have the link. This is the link. The question asks you to calculate the transmission rate of the link. Okay, so over here you have 4 channels. Each channel the rate is 1 kilobits per second. Okay, the question asks you the rate of the link. Okay, rate of the link. So the rate of the link, okay, question B is actually 4 multiplied with 1 kilobits per second. So this, the answer is 4 kilobits per second. And the third one, the duration of the time slot. Okay, so over here you have, you want to combine these 4 channels. So basically you have 4 frame like this. Because the question asks you the duration of a time slot. Okay, so to calculate the duration of the time slot for C over here. Okay, question C, duration for the time slot. Sorry, this one, the duration we represent as T. Okay, so the duration of a time slot is actually T over N. Okay, so just now we already calculated that the T is 0.001. So your N is 4. Okay, your N is 4. So your output is actually 250 microseconds. So this is the time, the duration of the time slot. Okay, and the last one is the duration of the frame. So the duration of the frame, this one actually should be like this. We have 4. Okay, because this is not in terms of bit, we don't know the number of bits here. Okay, so it should be like this. So this is one slot, and this is one frame. Just now we calculate the duration of one time slot. So it is 250 micro. Okay, and the duration of the time frame, this is actually equals to T. So question D, this is actually equals to T. T is 0.001 second. Or you can also, because you already know that one slot here is 250 micro, you can also calculate it as 250 micro multiply with 4 lah. So you will get back the T equals to 0.001 second. Okay. Okay, so the next example, you have 4 channels multiplex using TDM. Okay, channel 1, 2, 3, and 4. Each channel sends 100 bytes. Each channel sends 100 bytes per second. And we multiplex 1 byte per channel. Okay, we want to multiplex 1 byte per channel. Okay, show the frame traveling on the link, the size of the frame rate, duration of the frame, and the bit rate for the link. So the first question actually asks you to show the frame traveling, meaning you need to draw this. Okay, so to draw this, you should draw it like this. Okay, one frame like this. Okay, so each frame contains these 4 channels. So it will take 1 byte from each channel. 1 byte. So over here we have 100 bytes. Okay, so the first frame will take 1 byte from channel 1, 1 byte from channel 2, 1 byte from channel 3, 1 byte from channel 4. Okay, because you want to multiply it 1 byte per channel. Okay, so one frame consists of 4 byte lah. Okay, 1 byte from channel 1, 1 byte from channel 2, 1 byte from channel 3, 1 byte from channel 4. So remember just now, before this, I already told you that 1 byte is equals to 8 bits. Okay, so the size of the frame, okay, in terms of byte, it is 4 bytes, but in terms of bits, it is actually 32 bits. Okay, so it is actually how to get this 32 bits, it is actually 4 multiplied with 8. So you get 32 bits. Okay, so this is the size of the frame. Okay, the size of the frame in bytes and also in bits. Okay, the third question asks you to calculate the frame rate. The frame rate is 100 frames per second. Okay, how can we calculate the frame rate? Okay, so the frame rate, it is actually, you know that each frame consists of 1 byte. Okay, so over here you have 100 bytes each channel. So how many frames that you need in 1 second? Of course, it is 100, right? Because one frame is you only send 1. So you need to have 100 frames. So that's why the frame rate is equals to 100 frames per second. Okay, and then the bit rate. So the bit rate, this is the frame rate. This is the bit rate. Okay, so bit rate is the same this 100 frames per second, but in bits. Okay, but in bits. So what the thing that you need to do is that you just calculate it like this. So the bit rate is actually you have 100 frame. Okay, so multiply with 32 because one frame is 32 bits. Okay, so you have uh, uh, 3,200 bits per second. Okay, and the frame duration you can actually calculate like this: 1 over 100 per 100 seconds. So this is the frame duration. Frame duration is this one, the duration of one frame. Okay, so the next example, you have a multiplexer combines 400 kilobits per second using a time slot of 2 bits. Okay, for this one, the difference is that it will take 2 bits for each frame. Okay, so frame 1, it will take 2 bits from the first channel, and then 2 bits from the second channel, 2 bits from the third channel, and 2 bits from the fourth channel. Okay, so the question asks you calculate what is the frame rate, what is the frame duration, what is the bit rate, and what is the bit duration. Okay, so for this one, the bit rate, okay, is actually you have 100 kilobits per second for channel, so it is actually 100 kilobits per second multiplied with 4. So your bit rate is actually 400 kilobits per second. For frame rate, this is in terms of bits. Now you want it to be in terms of frame. Okay, so you know that one frame over here, one frame consists of 8 bits. One frame consists of 8 bits. So this 400 kilobits per second, 400K divided with 8, you should get 500K. This is frames per second. This is the rate in terms of frame. And then if you want to calculate for the frame duration, okay, so frame duration is actually 1 multiply with the, sorry, this is 50K, 50K frames per second. So to calculate the duration, it is actually 1 divided with 50K. This is equals to 20 microsecond, and the bit duration is 1 divided with 400K. So this is 2.5 microsecond. Okay. Next, okay, so this one, I want you to do it by yourself. Okay, please do this. Please download this slide, the new slide. So you have a question here. So please do this by yourself. So this question, I will include it as one of the question in your assignment. Okay, this will become one of the question in your assignment. So assignment will consist of several questions, and this will be one of the questions. So please do it. Please try and do this by yourself. Okay. And okay, so remember in the previous slide, okay. Okay, so the first slide for the TDM, time division multiplexing, this one. Okay, so it is stated that it can be divided into two, synchronous TDM and statistical TDM. Okay, so what is the difference between synchronous and statistical TDM? Is that for synchronous, okay, this is synchronous TDM. Time slot is given even though there is no data. So meaning that you have 5 channels. Okay, so you have for channel 1 you have A1, channel B you have B1 and B2, channel C you don't have nothing. Channel D you have D1 and D2, and channel E you have E2. So the output here, okay, at the output, the first frame, it will take 1 bit from channel 1, 1 bit from channel B, C, D, and E. So what happens is that for the first frame, you have A1, B1, and then look at here, for channel C, you don't have anything here, but still for synchronous TDM, you will still have a time slot here, even though you don't have any data. And then you have D1, and then blank slot like this. Okay, different to statistical TDM, the slots are dynamically allocated to improve the bandwidth efficiency. So for statistical TDM, the first frame, it will become A1, B1, and D1. Okay, so it will skip the channel without any data here. Okay, same for the second frame, you have B2, D2, and E2. So by right, for the statistical TDM, the bandwidth is better compared to the synchronous, because the bandwidth will be smaller compared to the synchronous, because it skips the channels without any data. Okay, do you understand the difference between synchronous TDM and statistical TDM? Hello? Hello?
Yes.
Okay, so actually we have finished chapter 5, part 3. Okay, so when we have online class like this, please at least respond if I ask you anything. Okay, so we have finished chapter 5, part 3, and we will have another lecture session for chapter 5, and then we will basically we have finished after that one, we finish the syllabus for this subject, and then only then after the chapter 5 part 4, then only we will have a discussion on your midterm test. Okay, and also revision for your final exam. So any question before we end?
No.
No.
question,
No,
doctor.
Okay, so I think that's all for today. And we will continue next week. Okay, so that's it. Thank you very much.
Thank you, doctor.
Thank you.